about the direction cosines of the normal, then is the orthogonal projections of surface S, and then is the concept of the volume integral. So let's start with the direction cosines of the normal. So the remark is, if the outward normal to the surface S at P makes angles alpha, beta and gamma with the positive directions of the x, y and z axes respectively. That is, the outward normal is making angle alpha with the x-axis and making angle beta with the y-axis and making angle gamma with the z-axis, right? Then if I take the cosine of alpha, then that will be equal to L. And M is equal to taking the cosine with beta. And N is equal to taking the cosine with gamma. So then L, M, and these are the direction cosines of the normal, right? So therefore, N vector is equal to cos alpha I vector plus cos of beta j vector plus cos of gamma k vector, right? That is equal to cos alpha is L. So this is L I vector plus mj vector plus nk vector. In particular, if I take the dot product of outward normal vector with I vector, then that will be equal to, yes, what is n vector? It is cos alpha I vector plus cos beta j vector plus cos gamma k vector. Taking its dot product with I vector, that becomes cos alpha I vector dot product with I vector, that is cos alpha only, right? And cos beta j vector dot product with I vector, that becomes 0 because j vector dot I vector is 0 and k vector dot I vector is also 0. I vector dot I vector is 1. So that is why n vector dot product with I vector becomes cos alpha only, right? Similarly, taking dot product of n vector with j vector, that becomes cos of beta, and taking dot product of n vector with k vector, that becomes cos of gamma. So let f vector, which depends upon x, y, z, if I write this in its component, so that will be f1 I vector plus f2 j vector plus f3 k vector. Then taking the dot product of f vector with n vector, what is that? F vector is f1 I vector plus f2 j vector plus f3 k vector. So taking its dot product with n vector is L I vector plus m j vector plus n k vector. So this is equal to, okay, if you take the dot product, this will be f1l plus f2m plus f3n, right? So this is equal to f1, what is L? It is cosine of alpha. Cosine of alpha, right? So this is f1 cosine of alpha. Similarly, f2, what is m? It is cosine beta. So this is cosine of beta plus f3, it is cosine of gamma. So dot product of f vector with n vector is equal to, yes, let's write this again. f1 cosine of alpha plus f2 cosine of beta plus f3 cosine of gamma. So if I take the integral of the dot product of f vector with n vector, then that will be equal to, if I take this integral across S, so that will be equal to integral over S f1 cosine of alpha plus f2 cosine of beta plus f3 cosine of gamma ds. Please mark this as 1. Now cos alpha into ds. or ds cos alpha. That is what? That is orthogonal projection of area ds on yz plane, or it is also equal to dy dz, right? Similarly, what is ds cosine of beta? It is orthogonal projection of area ds on, yes, zx plane, which is also equal to dz dx. And then ds cos gamma, this is orthogonal projection of area ds on xy plane, and it is equal to dx dy, right? So this integral now becomes integral of the dot product of f vector with n vector ds across s, that is equal to, it becomes now double integral, right? So it is double integral over s f1. Instead of cos alpha ds, I'm writing dy dz. So it is f1 dy dz plus f2 dz dx plus f3 dx dy, right? Please remember this. Next remark is about for evaluating the surface integrals. So it is convenient to express them as double integrals taken over orthogonal projection of the surface S on one of the coordinate planes, right? Either xy, yz or xz, right? Okay, so let me take projection on the xy plane first. So this is possible if any line perpendicular to the coordinate plane that is chosen, suppose xy, meets the surface S in not more than one point. So let R be the orthogonal projection of S on xy plane, right? And let P be any point on the surface S. And let gamma is the acute angle which the outward normal at point P to the surface S makes with the z-axis, right? As the outward normal at the point P makes angle alpha with the x-axis, makes angle beta with the y-axis, and gamma with the z-axis. From here we know that ds cos gamma is dx dy, where ds is the elementary area of the surface S at the point P, right? So this ds is equal to dx dy divided by cos of gamma, right? And that is further equal to dx dy divided by, what can I write instead of cos gamma as? Yes, it is the dot product of n vector with k vector, right? So it is dot product of n vector with k vector. But I have to mention the mod over here because of the restriction of the sign of the outward normal, right? So mod is important to be taken here, where this k vector is the unit vector along the z-axis. Hence the integral over S and dot product of f vector with n vector ds, that will be equal to double integral f vector dot n vector, and what is ds? ds is dx dy divided by mod of dot product of n vector with k vector. So it is dx dy divided by mod of dot product of n vector with k vector, right? So this is the integral over surface R1. Let me mention this R1 for the xy plane, and is also equal to the double integral. If I consider the yz plane, then I will write here f vector dot n vector dy dz divided by, it is n vector dot product with I vector, right? And R2 is the projection of S on YZ plane. Similarly, the double integral over R3. What is R3? It is a projection of S on ZX plane. F vector dot n vector dz dx divided by mod of n vector dot product with J vector, where R1 is a projection of S on XY plane, R2 is a projection of S on YZ plane, and R3 is a projection of S on ZX plane. Please take this as your remark. Then is the volume integral. So let volume bounded by the surface S be V, and let the single valued function be f vector depending on x, y, z variables. Let's subdivide the volume V into n elements of volumes delta V1, delta V2, delta V3 up to delta Vn. Right? Okay. Let's take any arbitrary point P1 in the volume delta V1. Similarly, taking the point P2 in the volume delta V2 and any arbitrary point Pn in the volume delta Vn, right? Okay, so let P1, P2, P3 up to so on up to Pn be arbitrary points in delta V1, delta V2, delta V3, so on up to delta Vn respectively, whose coordinates are x1, y1, z1, x2, y2, z2, so on, xn, yn, zn, right? Let's define the function f depending upon the point Pr, any arbitrary point Pr. Let's say from this, let's take this point to be as Pr in the volume delta Vr. So we are defining f to be equal to f, and the point Pr is xr, yr, zr. Fine? Okay. And then if I take the sum on fpr delta Vr, where r is starting from 1 to infinity, that is, if I am having infinite number of arbitrary points, then all those points are in the infinite number of elements of volumes, right? Then if I take the limit, taking limit when n is tending to infinity, such that if I am having infinite number of arbitrary points, then I am having infinite number of volumes delta V1, delta V2 up to infinity. So many number of volumes, right? Then the largest of the volumes, delta Vr, that will be tending to 0, right? Then the limit, if it exists, is called volume integral of f over v and is denoted by triple integral on f x y z dv over v, right? Okay, thank you.